Hello dear students, today we are going to study a topic from second unit of engineering chemistry. Second unit is instrumental methods of analysis. Dear students, previously the analysis was carried out using the old methods. The old methods were with the help of indicators. The old methods were taking more time. Those previously used methods were less accurate, and sample required for analysis by these old methods was also more. In short, you can say the old methods of analysis were having some drawbacks. To overcome these drawbacks, modern methods were required. New methods were implemented, and these new methods are with some instruments. These methods are called as instrumental methods for the analysis. Number of instrumental methods are there like pH metry, potentiometry, conductometry. Out of this, in today's video, in today's session, we are going to study the analysis by conductometry. Particularly here we are going to study the conductometric titrations. So our today's topic is conductometric titrations. What are the learning outcomes of this today's session? Friends, after completion of this session, students should be able to understand how to calibrate the conductometer. You should be able to understand how to construct a conductivity cell. You should be able to use conductometer for performing various neutralization titrations. And you should be able to study the applications of conductometric titrations. So these are the learning outcome of the today's session. What content we are going to cover in this video, in this session? The list is mentioned here. What is a conductometer? Calibration of conductometer, principle of conductometric titrations, neutralization titrations using conductometry, advantages of conductometric titrations, and applications of conductometric titrations. So in this video we are going to cover these 6 things. So this is today's content. Conductometer. Friends, a digital conductometer is shown in the diagram here. A conductometer is nothing but a instrument which is provided with these 2 electrodes, and these 2 electrodes are generally made up of platinum strips. These 2 electrodes acts as anode and cathode. So when these 2 electrodes are dipped in any electrolytic solution, there is a development of a cell, and whatever electrical conductance is possessed by this electrolytic solution is shown in the digital form by this instrument. This is the conductometer. Calibration of conductometer. Now before proceeding to the experiment, before using this conductometer for our analysis, it needs to be calibrated. A calibration of a conductometer means what? To cross check it, to validate this meter whether it is working properly or not, whether it is giving good results or not. For that purpose, generally what is done, a 0.1 molar KCl solution is used. We know the 0.1 molar KCl solution is having its standard conductance 12.88 millisiemens. So at room temperature at 25 degrees Celsius, it is the conductance of 0.1 molar KCl. So these 2 platinum electrodes are dipped into the 0.1 molar KCl solution. When it is dipped in such a known conductance solution, then meter has to show a reading of 12.88 millisiemens. If the meter is showing a deviated reading, then here there is a calibration knob. Here there is a calibration knob which can be rotated. So by rotating that knob, we will adjust the reading on the display here 12.88. As we know, 12.88 is a standard conductance of 0.1 molar KCl. So rotate the knob so as to show the meter here a reading of 12.88 millisiemens. Once the meter shows that conductance, then the meter is said to be calibrated and it is ready for further use. So this is called as calibration of conductivity meter. Next, principle of conductometry. Students, a simple principle is there used in the conductometry, and the principle is nothing but the factors affecting conductance. Electrolytic solutions are capable of conducting the current because of movement of the ions. The cations move towards the negatively charged electrode and anions move towards the positively charged electrode in the solution. So the movement of ions causes the movement of electrons, and that actually give rise to the electric current. Now this electric conductance of the electrolytic solution is affected by 4-5 factors, out of which these 3 main factors are used in conductometry. The 3 factors are: first one, the number and charge on the free ions in solution. The conductance of the solution depends on the number of ions present in solution and charge present on these ions. The conductance is also affected by mobility of these ions in the solution, and the conductance is also affected by size of these ions. Now let us see one by one how the number and charge affects. Number: as the number of ions in solution are more, the electrical conductance of that solution will be more. The charge present on the ion is more, then the conductance of that electrolytic solution is also more. So higher the number of ions, greater is the conductance; lesser the number of ions, lesser is the conductance. More the charge on ion, greater will be its electrical conductance; lesser the charge on ion, lesser will be the electrical conductance. Second factor, mobility of ions. As the ions are greater mobile, they are moving faster, they will cause more extent of electric current. So as the mobility of ions is more, electrical conductance of that electrolytic solution will be more. And the third factor is size of the ions. Actually, mobility of ions is affected by the size of that ion. Smaller the size of ion, greater will be its mobility, and indeed greater will be the electrical conductance. Smaller size ion is capable of moving fast, thereby causing more electrical conductance. Whereas a larger size ion will be lesser in mobile, and that will obviously give rise to less conductance. So these 3 things are used in the conductometric analysis, and these 3 things are actually the factors affecting electrical conductance. Listen once again how the electrical conductance is affected by these 3 factors. First one, the number and charge on the free ions in solution. More the number of ions present in solution, more will be the electrical conductance. Less the number of ions present in the solution, less will be the electrical conductance. More the charge on ions present in the solution, more will be its electrical conductance. Lesser the charge on ions, less will be the conductance. Mobility of ions: greater the mobility of ions, greater will be the electrical conductance. Lesser the mobility of ions, less will be the electrical conductance. Size of the ions: larger the size of ion, less will be its mobility, less will be electrical conductance. Smaller the size of ion, greater will be its mobility, faster will be the mobility, and greater will be the electrical conductance. So we can say this mobility and size are interrelated. Less size, small size, greater mobility, more conductivity. Larger size, less mobility, less conductivity. So these 3 things are used in the conductometric analysis. Next, conductometric titrations. Friends, as earlier told, previously to conduct the titrations, indicators were required, and those analyses were having the drawbacks. In fact, for certain titrations, indicators were not available. Indicator method is applicable for only those solutions which are colorless. For colored solution, indicator method is difficult to implement, and for that the conductometric titrations can effectively be implemented. So the definition for a conductometric titration is the titration whose end point is determined by measuring the conductance of electrolytic solution under study are called as conductometric titrations. Means those titrations whose results, whose end points, whose neutralization points, whose equivalence point will be determined by measuring conductance of electrolytic solution, whichever will be under study, is called as conductometric titration. Simplest definition that you can remember is the titration whose end point is determined by measuring the conductance of electrolytic solution are called as conductometric titration. Now conductometric titration can be commonly implemented for neutralization titration and precipitation titrations. Neutralization titrations are those which takes place between acids and bases, and precipitation titrations are those in which the product of the reaction is a precipitate. Particularly in today's video, in this session, we are going to study neutralization titrations by conductometry. We are going to focus only on neutralization titrations by conductometry. Next, neutralization titrations. As earlier told, the titrations between acids and bases, the reactions between acids and bases are called as neutralization reactions, and there are 4 types of neutralization titrations are there. These are strong acid versus strong base, weak acid versus strong base, strong acid versus weak base, and last one, weak acid versus weak base. Now this is actually based on the types of electrolytes. Friends, electrolytes are of 2 types, strong electrolytes and weak electrolytes. Based on that, the acids and bases are also categorized in 2, strong acids, strong bases, weak acids, weak bases. So in which particular type of acid is going to react with a base in that reaction, in that analysis, the neutralization titrations are possibly of 4 types: strong acid versus strong base, weak acid versus strong base, strong acid versus weak base, and weak acid versus weak base. These 4 neutralization titrations we are going to study. First from that is strong acid versus strong base titration. Now friends, in conductometry, generally the acids are taken in the beaker. During the analysis, the acids are taken in the beaker and bases are added from the burette. Now in case of titrations that you know, a burette solution will be there and a solution will be taken in the conical flask. Here instead of conical flask we use the beaker, as we are going to dip the platinum electrodes of a conductometer in that solution. So for the convenient, we instead of conical flask we use beaker. First conductometric neutralization titration is strong acid versus strong base. Example of a strong acid is HCl. Example of a strong base is NaOH, sodium hydroxide. As earlier told, generally acids are taken in beaker and bases are added from burette. So HCl will be taken in the beaker and NaOH will be added from burette. Now friends, in the beaker in the beginning only HCl is there. Okay, nevertheless NaOH is filled in the burette. So HCl being strong electrolyte, HCl is a strong acid, it is a strong electrolyte. So what about its dissociation? HCl will dissociate completely, and due to complete dissociation of HCl, the number of H plus ions in the solution of HCl will be more in number, and due to more number of H plus ions in the solution of HCl, the conductance of HCl in the beginning will be higher. So dip the electrodes, platinum electrodes of conductometer in the solution of HCl, and using the conductometer record the conductance without adding NaOH. Before adding NaOH, record the conductance of HCl. HCl being strong electrolyte, strong acid, more number of H plus ions will be there. In addition to that, H plus ions are smaller in size, greater mobile and greater conducting. So conductance of HCl in the beginning will be higher, more conductance will be there. Now from the burette, add a specific amount of NaOH. Now as soon as we add the NaOH from burette, neutralization reaction will occur between HCl and NaOH. The product of neutralization is NaCl and water. Here the H plus ions are replaced by what? Na plus ions. In this reaction of a strong acid strong base, H plus ions are replaced by Na plus. H plus ions were smaller in size. These are replaced now by Na plus ions, which are comparatively larger in size. H plus ions being smaller in size, they were greater mobile, greater conducting. Na plus ions are larger in size, lesser mobile, lesser conducting. So what it will result in conductance? It will result in decrease in conductance, because faster, greater mobile H plus ions are replaced by lesser mobile Na plus ions. The conductance will decrease. Here we continue adding NaOH and each time we record the conductance. After the sufficient amount of NaOH is added, we plot a graph of conductance along y-axis and volume of NaOH added along x-axis. So the volume of base added is plotted along this x-axis, and conductance of the HCl is plotted along the y-axis. Now it is observed that in the beginning the conductance of HCl is higher. When NaOH is added, when volume of NaOH is increased, the conductance decreases. This decrease in conductance is due to what? Replacement of smaller size, greater mobile H plus ions by larger size, lesser mobile, lesser conducting Na plus ions. So conductance will decrease. The conductance decreases up to specific point. After that, if we continue adding NaOH, the conductance increases. So after this point, on adding NaOH, conductance increases. So it is observed that in a graph of conductance versus volume of NaOH added, in the beginning the conductance is higher. That is purely attributed to strong electrolyte HCl. On adding NaOH, conductance decreases. This is attributed to replacement of H plus ions by Na plus. After this point, the excess added NaOH is there, due to which the conductance increases. At this point, the conductance is minimum, and the point corresponding to minimum conductance on x-axis, the volume is the volume of NaOH required to neutralize the HCl. In this way, we determine the neutralization point, end point, from the graph by plotting the conductance versus volume of NaOH added. The point of intersection of these two lines, or the point of minimum conductance corresponding volume on x-axis, is the end point of this titration. You can say a V-shaped graph is obtained for a strong acid, strong base neutralization titration. Now calculation part, it is a titration between HCl and NaOH. Consider N1, V1 are the parameters of HCl and N2, V2 are of NaOH. N1, that is normality of HCl, V1 is the volume of HCl, N2 is the normality of NaOH, and V2 is the volume of NaOH. Friends, whenever we analyze a sample, for analyzing that sample, the other species, we use a standard one. So suppose we are analyzing HCl. For analyzing HCl, we will use a standard NaOH. A standard species means what? Its strength is known, its normality is known. So here, suppose NaOH is standard, its normality is known. So what will we do? We will take a known volume of HCl for analysis. Whatever HCl will be taken for analysis, its volume will be known. So N1 is unknown as it is our sample. V1 will be known as whatever amount will be taken, that will be measured. N2, normality of NaOH will be known because it is standard, and V2, volume of NaOH, that will be obtained from graph. So with this we can find out the N1, that is normality of HCl, as N2V2 by V1. In this way we can find out the normality of any of the two species. Here it is for HCl, and after determining normality we can determine its strength by multiplying it with its equivalent weight. This is the first neutralization titration, strong acid against strong base. Second neutralization titration, weak acid versus strong base. The example of a weak acid is acetic acid, CH3COOH. An example of a strong base is NaOH. So as earlier told, generally acids are taken in beaker and bases are added from burette. So for this titration, CH3COOH, acetic acid, will be taken in beaker and NaOH will be added from burette. Now as same as that of the previous one, in the beaker we have the acetic acid, burette will be filled with NaOH. Now acetic acid is weak electrolyte, so its dissociation will be up to lesser extent, so it will give less number of H plus ions, and due to less number of H plus ions given by acetic acid, the conductance of acetic acid in the beginning will be less. During titration we are going to add NaOH from burette. When NaOH is added from burette, the neutralization of acetic acid will start, and the product of neutralization will be sodium acetate and water. Now friends, here also H plus ions are replaced by Na plus. Smaller size ions are replaced by larger size. So it is expected that the conductance should decrease, but here the product formed here is a strong electrolyte. Sodium acetate formed here is a strong electrolyte which dissociates completely, and due to complete dissociation it gives more number of CH3CO minus and Na plus ions. Due to more number of these ions, conductance increases. So instead of decreasing conductance on adding the NaOH, conductance increases, but the increase in conductance is observed to be gradual. So it increases gradually, slowly. Up to what stage it will increase gradually? Till there is acetic acid in the beaker. If you continue adding NaOH from burette, after a particular point the conductance increases sharply, conductance increases abruptly. This is because the whatever acetic acid was there, that got neutralized up to this point. After this point there is only excess added NaOH. So here the conductance is purely due to acetic acid. Here gradual increase in conductance is showing neutralization of acetic acid, and after this point it shows excess added NaOH. So here gradual increase and sharp increase, two lines are obtained, and the point of intersection of these two lines corresponding volume is the end point of the titration. So this is the volume of NaOH required to neutralize the acetic acid. So the nature of graph is shown here: gradual increase, sharp increase in case of a weak acid versus strong base titration. The calculation is done in the similar way as it was done previously for strong acid, strong base. Third, strong acid versus weak base neutralization titration. The example of a strong acid is HCl. The example of a weak base is NH4OH. Acids are generally taken in beaker, so HCl will be taken in beaker. Bases are added from burette, so ammonium hydroxide NH4OH, weak base, is added from burette. Now in the beginning HCl will be in the beaker, being strong electrolyte, strong acid, it will dissociate completely. complete dissociation of HCl will give more number of H plus and Cl minus ion. So what about the conductance of HCl in the beginning? It will be more, higher will be the conductance. When we add ammonium hydroxide from burette, the reaction occurs between these two, causing the neutralization of HCl, and product is NH4Cl and water. Here when we add NH4OH from burette, the NH4 plus ion replace the H plus, due to which it is smaller size H plus ions are replaced by larger size NH4 plus, due to which the conductance decreases. The decrease in conductance is sharp. This is attributed to which thing? Replacement of smaller size, greater mobile, greater conducting H plus ions by larger size, lesser mobile, lesser conducting NH4 plus ions. So addition of NH4OH in HCl leads to sharp decrease in conductance, and this decrease shows what? Neutralization of HCl. Up to what stage it will decrease sharply? Till there is HCl. Once all HCl got neutralized, after that there is only excess added NH4OH, which is a weak electrolyte, which is not going to affect the conductance that much more. So conductance will either remain same or it will slightly decrease. When we plot a graph of conductance versus volume of NaOH added for such type of titration, strong acid versus weak base titration, the nature of graph is sharp decrease and then constant conductance or gradual decrease. The point of intersection of these two lines will be obtained. The point of intersection of these two lines and the corresponding volume will be the volume of NH4OH required to neutralize the HCl. That will be the end point of the titration. The calculations will be HCl versus NH4OH, and this will be performed as that of the strong acid, strong base. Last and fourth, weak acid versus weak base neutralization titration. The example of a weak acid is acetic acid. Example of a weak base is ammonium hydroxide, NH4OH. Acetic acid will be taken in beaker, NH4OH base will be added from burette. So in the beginning, beaker will contain only acetic acid, which will have acetate anion and H plus ion cation. Being weak electrolyte, it will dissociate up to lesser extent, so less number of ions will be there, due to which the conductance of weak acid, acetic acid will be less. It will be less when NH4OH is added. Now here added electrolyte, added base from burette is also a weak electrolyte. So this is a reaction of the type of weak electrolyte versus weak electrolyte, weak acid versus weak base. The product of these two, weak acid and weak base, is a strong electrolyte, ammonium acetate. So in the beginning, acetic acid with less number of ions, with less conductivity is there, which will be reacted with NH4OH from burette. When NH4OH is added, that will lead to form the ammonium acetate, which is a strong electrolyte, which will dissociate completely. So due to complete dissociation of ammonium acetate, more number of acetate anion and NH4 plus cation will be obtained, conductance will increase. So when during neutralization is there, the conductance increases. Up to a particular point, conductance increases. After that it remains same or it increases gradually. The point of intersection of these two lines, corresponding volume, is the end point of titration, that is V2 ml, that is the volume of NH4OH required to neutralize the acetic acid. So the nature of graph obtained here is, in the beginning for acetic acid conductance is less. On adding NH4OH, strong electrolyte will be formed, so conductance increases sharply. After the end point, either conductance remains same or in some cases it increases slightly. So these two lines will be obtained, the point of intersection of these two lines, and corresponding volume on x-axis will be the volume of base required to neutralize the acetic acid. So it is CH3COH versus NH4OH. From this, N1 mu1 is equal to N2 we do, we can perform the calculation and we can find out the normality of acetic acid and later on its strength by multiplying it with equivalent its equivalent weight. Friends, particularly this fourth weak acid versus weak base type of titration is very difficult to perform by using indicator method, as indicator method does not give any result for this titration. It is successfully can be performed with conductometry. So here we have studied total 4 neutralization titrations. These are strong acid versus strong base, HCl versus NaOH. The nature of graph is V-shaped. Second one, weak acid versus strong base, acetic acid versus NaOH. The nature of graph is gradual increase and sharp increase after end point. Third one, strong acid versus weak base, HCl versus NH4OH. In terms of example, the nature of graph is sharp decrease of conductance up to end point and after end point either remain same or gradual decrease. And in case of weak acid versus weak base, the examples are acetic acid versus ammonium hydroxide NH4OH. The nature of graph is sharp increase up to end point, gradual increase or almost same after end point. The point of intersection of these two lines will give the end point. In this way, by plotting the graphs of conductance versus volume of burette solution added, we can determine the end point. From the end point, we can do the calculations to find out the normality of either of the acid or base, which can be used to find out the strength by multiplying the normality with equivalent weight. This is about the neutralization titration using conductometry. Advantages of conductometric titrations. In what aspect these titrations are advantageous over the old methods, old titrations? First one, these titration does not require indicator. No use of indicator is there. This is because conductance is measured by using the conductometer. So this is first and important advantage of these titrations is there. This does not require indicators, as conductance measurement is implemented for finding the end point. Second one, applicable for colored solutions also. Third one, these titration gives accurate results. Quick and accurate results are obtained by this method. These titrations are applicable for turbid solutions, weak acids and weak bases. And conductometric titrations are those in which the amount of sample required is less. So in old methods of analysis, sample required is more, whereas in these techniques, in these methods, sample required is less. So these are some notable advantages of conductometric titration. This does not require indicator. These are applicable for colored solutions also. Accurate results are obtained. These are applicable for turbid solution, weak acids and weak bases, and the amount of sample required for analysis is less. Applications of conductometry is the last part. Conductometry finds the applications in number of forms. Number of applications are there. The list of some important applications is mentioned here. First one, to perform the neutralization titrations. Second, to perform the precipitation titration. Third, to study the chemical equilibrium in ionic reactions. Fourth one, to study solubility of sparingly soluble salt. And last one, to study the basicity of organic acids. For these applications, the conductometric titrations, the conductometry is used to perform the neutralization titrations, to perform this precipitation titration, to study the chemical equilibrium in ionic reactions, to study the solubility of sparingly soluble salts, and to study the basicity of organic acids are the applications of conductometry. Thank you all of you. Thank you very much.